Welcome to the video lecture series of solid state devices. Course code EC301. The course is metal oxide semiconductor field effect transistor, MOSFET. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department, Guru Nanak Institute of Technology, Kolkata. This is Module 4, Field Effect Transistor, and the lecture number is 12. So Module 4 consists of metal oxide field effect transistor, types of MOSFET, structure of MOSFET, MOS structure under external bias accumulation, depletion inversion phenomena with energy band diagram, threshold voltage and flat band voltage, working of MOSFET with characteristics, drain current equation for linear and saturation region, derivation of threshold voltage of ideal and non-ideal MOSFET, MOSFET capacitance, different types of MOSFET capacitance, MOS capacitance variation with gate to source voltage under low frequency and high frequency, large and small signal model of MOSFET, explanation with diagram, numerical problem. This lecture particularly inclined to types of MOSFET, structure of MOSFET, MOS structure under external bias accumulation, depletion and inversion phenomena with energy band diagram. So why MOSFET? FETs have few disadvantages like low input impedance, high drain resistance and slower operation. To overcome these disadvantages, the MOSFET, which is in advance of FET, is invented. MOSFET stands for metal oxide semiconductor field effect transistor. And the MOSFET operates both on enhancement mode and depletion mode. Enhancement mode MOSFET can be further classified as P-channel and N-channel MOSFET. Depletion mode can be further classified as P-channel and N-channel MOSFET. So basic construction of MOSFET. In JFET, we have seen that N-channel, for an N-channel JFET, N-channel was there, gate terminal was there, that is heavily doped, drain, source, gate, both are there, metal contacts are there to take out the contacts. But the thing is that this SiO2 layer between the gate terminal and the bulk silicon or the channel was not there. That is omnipresent in, that is actually present only this MOSFET. That's why the name, this is metal, this is oxide, this is semiconductor. Metal, oxide, semiconductor, FET. This oxide terminal is only at the deposited at the gate terminal or the beneath of the gate terminal. No drain and source terminal are associated with this SiO2 layer. So this is the construction of N-channel MOSFET and this is the construction of P-channel MOSFET. Here we, for P-channel MOSFET, same thing we are seeing, that SiO2 layer is there between gate terminal and the channel, and this is the substrate, SS substrate, this is gate, this is drain, this is source, and this is the substrate. Substrate actually connected to the gate terminal. So symbols of N-channel MOSFET, symbols of P-channel MOSFET. So symbols of N-channel MOSFET, enhancement mode, depletion mode. This is enhancement mode and this is depletion mode. This enhancement mode MOSFET, this line is discontinuous, where in depletion mode MOSFET, this line is continuous. The only difference between these two. Why? Because in depletion mode MOSFET, actually diffused channel or a channel between drain and source terminal is already there at the time of fabrication. So the channel is continuous. Already there is a fabricated channel between source and drain. Whereas for enhancement type MOSFET, there is no channel present between source and drain at zero bias condition or at the time of fabrication. That's why as the channel is discontinuous in enhancement mode MOSFET, that's why this line is broken here. But in depletion mode MOSFET, as there is already a channel exists between drain and source, that's why this line is made continuous. That is, drain and source is continuous through this channel. Similarly, for P-type MOSFET, the same symbol, but the arrow is down outward for P-channel MOSFET and arrow is inward for N-channel MOSFET. So depletion type MOSFET actually normally on. It is written over there. This is normally on. That means a channel already is there when there is zero bias. So minimum current can flow between drain and source through the channel. So that's why this type of MOSFET is called normally on. On the contrary, enhancement type MOSFET is called normally off as there is no channel. So no current is flowing through the channel when zero gate to source voltage is applied. Whereas for depletion mode MOSFET, there can be a current flow when zero gate to source voltage is applied as there is a channel present between gate and source. Hope this is clear. So this is the difference between MOSFET and BJT. BJT, three different currents in the device: IC collector current, IB base current, IE emitter current, consume a lot of power and large size of the device. But for MOSFET, mostly widely used today, this device, this is of low power, this is of small device dimension of the order of nanometer. 1 nanometer, 2 nanometer level MOSFET is also available in the market nowadays, and simple manufacturing process. And the main thing is, in BJT there was three currents present in the device, but in MOSFET only one current, that is drain current, is present in the device. So MOS field effect transistor. In the MOSFET, the current is controlled by an electric field applied perpendicular to both the semiconductor surface and to the direction of current. The phenomena is called field effect. The basic transistor principle is that the voltage between two terminals provides the electric field and controls the current through the third terminal. So I repeat, the basic transistor principle is that the voltage between two terminals provides the electric field and controls the current through the third terminal. So that is happening in case of two terminal metal oxide semiconductor field effect transistor. A MOS capacitor with a P-type semiconductor substrate, the top metal terminal called the gate is at negative voltage with respect to the substrate. So this is the gate metal, this is the SiO2 layer, and this is the P-type substrate. So this side is positive, this is a metal layer, this is semiconductor, this is obviously full conductor, this is semiconductor. So we can consider it as a parallel plate capacitor. So parallel plate capacitor means these two plates, this metal plate, this metal plate, and the semiconductor, bulk semiconductor, is separated by the oxide layer, that is dielectric layer. So as per the rules of the capacitor, if this side is negative, this side should be positive. It is shown over there, accumulation layer of holes in this side. So a negative charge will exist on the top metal plate and electric field will be induced. If the electric field penetrates the semiconductor, the holes in the p-type semiconductor will experience a force toward the oxide semiconductor interface and an accumulation layer of holes will generate or will be developed. So here we can see accumulation layer of hole has been generated when negative voltage is applied at the gate terminal. So the same MOS capacitor but with the polarity reversed. If this side is positive, then this side obviously negative, because negative charge will be induced at the bulk semiconductor. A positive charge now induced in the electric field in the opposite direction. The electric field was upward direction. But here the electric field is downward direction. The electric field penetrates the semiconductor. Holes in the p-type material will experience a force away from the oxide semiconductor interface. So as the holes are pushed away from the interface, a negative space charge region is created when positive voltage is applied at the gate. So this region of minority carrier electrons is called electron inversion layer. In case of previous one, that means when negative voltage was there at the gate terminal, then hole inversion layer was created. But when we are using positive voltage at the gate terminal, then electron inversion layer is created. First accumulated, negative charges are accumulated at the oxide semiconductor interface, then inversion layer is created. So first accumulation, then inversion. The magnitude of the charge in the inversion layer is a function of the applied gate voltage. Hence, the larger voltage is applied, the wider it becomes. So this is first accumulation, first induction, then accumulation, then inversion. So this is electron inversion layer, and previously it was hole inversion layer. Now construction of an N-channel MOSFET. Here we can see that this is p-type substrate. This is N+, that means this drain and source regions are heavily doped, whereas substrate is bulk semiconductor, moderately doped. N-channel region between source and drain. For positive gate voltage, depletion region is populated by negative charges. For positive gate voltage. Now drain and source are heavily doped. P-channel region between source and drain. Apply the negative gate voltage, electron pushed downwards. Depletion region is populated by the bound positive charges. Just reverse of the previous one. The flow of current is positively charged holes. And in previous case, the flow of current was for negatively charged electrons. So the aim of MOSFET is to control the voltage and current flow between the source and drain. It works almost as a switch. So the MOS capacitor is the main part of the MOSFET, as already discussed. New schematic has been presented here. So when gate is negative, this region is SiO2 layer, this region is negative, and when gate is positive, then SiO2 layer end is, when this region is negative, this region is negative, and when this region is positive, SiO2 semiconductor interface layer is also positive due to the induction mechanism. So, in depletion mode, when there is no voltage on the gate, the channel shows maximum conductance. As the voltage on the gate is either positive or negative, the channel conductivity decreases. But for enhancement mode, when there is no voltage on the gate, the device does not conduct. More is the voltage on the gate, the better the device can conduct. So depletion mode operates in depletion mode the same way as JFET, that is when VGS is less than 0, less than equals to 0. And MOSFET operates in enhancement mode when VGS is greater than 0 or VGS is greater than V threshold. So enhancement mode MOSFET or eMOSFET. The schematic symbol for the N channel and P channel MOSFET is shown in the figure below. This is N channel enhancement type MOSFET. This is P channel enhancement type MOSFET. Enhancement mode with the positive gate voltage, more conduction electrons are attracted to the channel, thus increasing the channel conductivity. So enhancement type MOSFET can be described as, the figure shows the construction of enhancement type MOSFET. Here, the main difference between the construction of DE MOSFET and the E MOSFET is that the E MOSFET substrate extends all the way to the silicon dioxide and no channels are doped between the source and drain. That is, substrate is extended to the silicon dioxide end. No channel is there. But for depletion type MOSFET, the semiconductor material is not connected or is not extended to SiO2 up to SiO2 layer, because prior to that one channel is existing between SiO2 and the bulk silicon. The source and drain are taken out through metallic contacts to end-doped region. These end-doped regions are not connected via an N channel through an external voltage. The gate connects to the p-doped substrate via a thin insulating layer, SiO2. Channels are electrically induced in these MOSFETs when a positive gate source voltage VGS is applied to it. So when this is positive, this side is negative, so a channel is developed between source and drain. So this MOSFET operates only in enhancement mode and never in depletion mode. It operates with large positive gate voltages only. When drain is applied with positive voltage with respect to source and no potential is applied to the gate, a very small drain current, that is reverse leakage current, flows. The enhancement MOSFET does not conduct when the gate source voltage VGS equals to 0. This is the reason why this device is called normally off MOSFET. So we can see gate positive means negative channel, negative charges are induced and electrons are flowing from source to drain when we apply the external bias. This gate source is reverse biased and the VDS is connected, drain is connected to the positive terminal of the battery and a source is connected to the negative terminal of the battery. This is N channel enhancement type MOSFET. So when the gate is made positive with respect to source and the substrate, negative charge carriers within the substrate are attracted to the positive gate and accumulate close to the surface of the substrate. As the gate voltage is increased, more and more electrons accumulate under the gate. Since these electrons cannot flow across the insulated layer of silicon dioxide to the gate, so they accumulate at the surface of the substrate just below the gate. When this occurs, a channel is induced by forming what is termed as inversion layer. Now a drain current starts flowing. So the enhancement mode MOSFET operates only in enhancement mode. VGS is always positive, IGSS is 0 when VGS is less than V threshold. When VGS is greater than V threshold, the device turns on and the drain current ID is controlled by the gate voltage. As VDH increases above VT, the density of electrons in the induced channel increases and ID increases. If VGS is kept constant and VDS is increased, then ID saturates. The almost vertical components of the curves corresponds to the ohmic region, and the horizontal component corresponds to constant current region. The MOSFET can be operated as in either of this region, that is constant current region or to the ohmic region, and can act as a voltage variable resistor, that is VVR, and as a constant current source. This is the drain characteristics of enhancement type MOSFET. We have applied positive gate voltage here and we are getting drain current. MOSFET transfer characteristics. The MOSFET for all practical purposes does not conduct until VGS reaches the threshold voltage VGS-TH. ID when conducting can be determined by the formulas below. The formula is K equals to ID on by VGS minus VGS threshold whole square, or ID equals to K into VGS minus VGS threshold whole square. K is a constant. N-channel device requires a positive gate to source voltage and P-channel device requires negative gate to source voltage. So what is threshold voltage? IDSS at VGS greater than equals to 0 is very small. VGS made positive, current increases slowly. ID on corresponds to maximum value of drain characteristics. Plus 12 volt generates supply voltage for N-channel MOSFET. Compatibility issue with BJT is there. Many techniques adopted to reduce the threshold voltage. So lowering the magnitude of VT. One is silicon wafer that should be of 100 type. That means low packing density. If the packing density is low, then the threshold voltage can be reduced. But if the packing density is high, that means if we use 111 silicon wafer, then much more voltage is required to exceed the V threshold. Use composite layer of dielectric whose dielectric constant is about twice that of SiO2 alone. Then also V threshold can be decreased. Boron doped polycrystalline silicon can be used as gate material. So this is the schematic of P-channel enhancement type MOSFET. The P-channel enhancement MOSFET similar to N-channel except that the voltage polarities and current directions are reversed. Here we can see VDS versus ID, that is output drain characteristics, and here we can see VGS versus ID, that is transfer characteristics curve. In earlier, this was the transfer characteristics curve, VGS versus ID, that is in the first quadrant because VGS and ID both were positive. But in this case, we can see that VGS is negative and ID is positive. ID is negative. VGS is negative and ID is also negative. This is for P-channel MOSFET. So this is the comparative study of JFET, DMOSFET and eMOSFET. We have already learned how to draw the transfer characteristics of JFET. The same concept can be applicable here also. For eMOSFET, the drain current formula is this one, but for DMOSFET is similar to JFET. Same formula has been used here. So for eMOSFET, there is one thing, that is V threshold is required to make the device on. But in case of DMOSFET, as already there is a channel, when there is no bias is applied, still there is a current flow through the device. That is because of the already fabricated channel. That's why this current is showing here. And as we keep on decreasing the gate to source voltage, then a point reach when VGS equals to minus VP, then the device is cut off. So these are the reading materials. If there is any question, please contact to this email ID. Thank you.